Welcome everyone to this poster presentation, which will be about a new method for solving partial observable stochastic games while having theoretical guarantees and being computationally scalable. My name is Kim, and this is joint work together with Tansu. So here we focus on partial observable stochastic games that are zero-sum and have one-sided partial observability, which means that it is a dynamic game between two players where player one has partial observability about the state of the game and player two has perfect observability. The current methods for solving this type of games can be divided into two main categories. So on the one hand, we have heuristic search value iteration, or HSVI. And this is the current state-of-the-art method in the sense that this is the only method that has theoretical guarantees for solving the game. On the other hand, this method is not very scalable and is currently limited to very small game instances. On the other hand, we have deep reinforcement learning methods, such as NFSP. And these methods are very scalable, but they have no theoretical performance guarantees and tend to not work very well in practice. So in this work, we try to address these limitations by presenting a new method, which we call Shapley iteration with aggregated beliefs, or SAB or SAB for short. And this method consists of three main steps. First, we convert the original game into an aggregate belief game by aggregating the belief space of the original game into a finite set of representative beliefs. Then we solve the aggregate belief game using Shapley iteration. And finally, we use the solution to the aggregate belief game to approximate a solution or a value function for the original game via interpolation. And this method has two big advantages. One advantage is that it is a very flexible method in the sense that we can adjust the aggregation of the belief space based on the available computational resources and based on structural properties of the game. And the other big advantage of this method is that it has strong theoretical guarantees. So it is a principled method. And in particular, we prove in the paper that SAB is guaranteed to converge for any partial observed stochastic game with a finite state and observation space, as illustrated in the figure here, where the curves relate to different sizes of the aggregate belief game, so different number of aggregate or representative beliefs. We also prove that the value function, the approximate value function that we obtain from our method, which I denote here with v tilde, the difference between that value function and the true value function of the game, which I denote with v star, is bounded by this inequality here, where gamma is a discount factor of the game and epsilon is the maximum variation of the true value function within each partition of the belief space that map to the same representative belief in the aggregate belief game. And all of the details about this proposition and also the previous proposition is available in the main body of the paper. To evaluate our method experimentally, we apply it to three different example games, namely a pursuit evasion game, a patrolling game, and a stopping game. And we start by comparing the performance of our method with the current state of the art, namely the HSVI method. And by necessity, we do this comparison on relatively small games, since HSVI cannot be applied to large game instances. So here, each row relates to a different game, and the columns relate to different sizes of the game, which is controlled by this parameter here, n. The performance of our method is shown in blue, and the performance of HSVI is shown in red, where on the x-axis you have the computation time, and on the y-axis you have the approximation error. So the difference between the approximate value function computed by SAB or HSVI and the actual value function. And what we can observe here is that both methods converge as we allow more computation time, as expected from the theory. However, our method converges significantly faster than HSVI. And this is also clearly illustrated in the following bar plot, where we have computed the aggregate time or the average time to reach a low approximation error across all games. And what we can see is that on average, our method reaches a low approximation error 80% faster than HSVI. So our method both is more computationally efficient than HSVI, has similar theoretical guarantees, and it is also more scalable. And to illustrate the scalability, we have applied our method to a large game instance where we cannot apply HSVI because HSVI is limited to relatively small games. So for that reason, we instead compare our method with neural fictitious self-play, or NFSP, which is a deep reinforcement learning method. Here on the x-axis, you have the computation time, and on the y-axis, you have the exploitability. So a lower exploitability means that we are closer to converge to an equilibrium, so closer to converge to a solution of the game. So we want the exploitability to be as low as possible. And what we can see here is that our method converges much, much faster than NFSP. And we attribute this fast convergence due to the ability of our method to exploit structural properties of the game when we create this aggregate belief game. So in conclusion, we present a new method for solving partial observable stochastic games, which we call Shapley iteration with aggregated beliefs, or SAB for short. Theoretically, we prove that SAB is guaranteed to converge, and we also establish a bound on the approximation error. Experimentally, we have demonstrated that our method outperforms the state-of-the-art methods for these type of games across 3 different types of game instances. And for more details about this work, please see our paper, and we look forward to see you at the poster session in Singapore. Thank you very much for your attention.